Okay, first up is the 2 Charlie identify basic facts about electromagnetic loss theory. Remember, you got 70% to get on your KPC, AFSC application. Whole idea behind it is understanding your losses as well as what's happening in the ionosphere during the day and during the night. We're going to look at path loss, atmospheric attenuation, multipathing, free space loss, and anomalous propagation. First up is path loss. What does it mean? It means that the difference between the power transmitted versus the power received. Idea here is I'm going to transmit out 10 watts. The whole idea is I'd like to see 10 watts get to the distant end, but that doesn't happen because of the environmental and a lot of other different happens. If you have free space in there, you're probably going to see a spread, and we'll see free space loss here in just a few. So 10 watts, you're probably going to see about 100 milliwatts, and that's about normal when you're looking at the distance. Atmospheric attenuation, this is caused by moisture. Attenuation increases if the frequency increases. In other words, if you're in the HF area, the rain and that don't really affect it as much, whereas the upper frequencies, it does. For those of you who've ever had Dish Network or DirecTV, what happens when there is a hard rain? You probably lose your signal, and that's because of the tropospheric scintillation is a portion of it. This one is when you have random pockets of air. There are, as you go in altitude, there's differences in your humidity, temperature, and things like that. Uh, what it does cause to the waveform is the amplitude or fluctuation of the phase. Multipathing, this is an example of when you have multiple signals going and hitting and reflecting off of buildings and things like that, off of, say, a mountain. Just some examples. We call that fading. What does it sound like? It sounds like you're in control of the volume control button and you turn the volume down just where you could barely hear it and turn it back up again and then turn it down. That's what fading sounds like. It is a problem for items like AM and HF, but the better the equipment, the more that it can eliminate that fading. Here is another part of how this multipathing happens, and your receive signal starts going a little nuts. You can see the differences in the time that's being received and what the combined results are. We look at free space loss. This is in that theoretical perfect space, free of everything. The idea is when I'm transmitting, there will always be a decay in the radio wave due to the distance. Free space loss, again, it's a reduction of signal strength, not to be confused with path loss. Path loss is that distance between the two. Just remember, they can be combined together. IEEE did it back in, I think, 97, and we're just now seeing the results of the IEEE coming out over the internet, and they did combine path loss and free space loss, so don't worry about it because there's also something called a Fresnel, how you pronounce it, equation that goes with it, explaining as you go out the spread, it's also segregate as you go time. Add the environmental in there, and it really gets what we call a major signal loss. We have anomalous propagation. This one means it doesn't follow a straight line. Oh, gee. Could be reflection, refraction, and diffraction. And what's it called? Tropospheric scintillation is another example with that density variation like that. Again, tropospheric scintillation, we're just going back over the information because that's what happens to some of the signal. All right, we've gone through path loss, atmospheric attenuation, multipathing, phase loss, and anomalous propagation. That was pretty doggone quick.